I'm just going to say we have Gigi here from Princeton, and he's going to talk about multi-agent reinforcement learning. Thank you.
Okay. Hello, everyone. I'm Gigi. Actually, thanks for inviting me to give this tutorial at Simon's Bootcamp. So today I'm going to talk about the multi-agent reinforcement learning. I hope you guys learned a lot about reinforcement learning this morning from Dylan's talk. So yeah, I'm gonna build up on a little bit on that, and also probably more on what we have learned in the past few days in game theory, and then we're gonna go for multi-agent reinforcement learning. I'm from Princeton, and the slides is on my homepage. It should be fairly easy to find it on my homepage. And also we have similar contents is already on the blog post, which is written by you and me on this website. First, I want to thank a lot of the contributors. The contents that present a lot of results are from my group, also from these contributors. It's kind of like the knowledge we gather together, we work together over the past few years. And they are Yu Bai from Salesforce, and Qinghua Liu from Princeton, Yuanhao Wang from Princeton, and also Tianchen Yu from MIT. First, let's motivate why we want to study the multi-agent reinforcement learning. If we kind of consider back again, what are the really biggest success over the past few years, like in reinforcement learning or in the field of AI, you might come up with okay, the game of Go, and also StarCraft 2, and even some Texas poker, where basically human already built some intelligent agents, which is able to beat the world champion on those games, which were thought to be super hard. If you consider a little bit more about all those kind of games, they actually has two properties. One is they are kind of involve multiple agents. It's not like a single agent. It's not a single player playing the game. It's kind of like you need at least two players. It's kind of like multi-agent games, so it definitely involves some game theory. And the second part is not only a simple game. It's actually a game that involves a sequential decision making. So it requires you to make a sequence decision and see the feedbacks of the other players, and then build on those feedbacks and make the other decisions. So we can see that all those games kind of consist of these two parts. So we can look at the theory of both of them, each of them. The first one is we look at the classical game theory. Classical game theory, I guess also some of the topics of what you have already heard in the past few days are about normal form games or extensive form games. Normal form games are those games which basically you can represent the entire game reward as a matrix. So all the players just play simultaneously, and then this game is done. So there's no sequential information, or there's no time series at all involved in this normal form games. Extensive form games is a little bit better, and actually extensive form games is pretty good in modeling those poker games, where essentially they model the game as a tree. So each player take actions, and you follow the path of those actions and go to leaves, and you receive the rewards. However, we notice one a little bit inefficient part about the extensive form game is it's kind of grow exponentially with depths. Okay, the size of trees grow exponentially with depths. So for a lot of the games we're playing, for example, StarCraft, we're gonna play this game for 20 minutes, and each minute we're gonna play probably 60 actions. So the size of the game tree is gonna explode on gonna grow exponential on the length of the horizon. So this extensive form game is extensive form games is not very efficient in representing those kind of sequential games, especially with a very long horizon. On the other hand, we say one is about multi-agent game, the other one is about sequential decision making. So there actually exists a framework called reinforcement learning, which just basically entire field is built on dealing with those sequential decision making problems. So it has an agent, it will interact with the environment. So agent will feed the action to the environment, while environment will feed back the states and the reward, so that there's a loop going on between the agents and the environment. It's kind of interaction. So the goal of the agents in reinforcement learning is to try and find the best policy within a fixed environment. Okay, so this is actually the goal of single agent reinforcement learning. And all the algorithm is designed based on the assumption the environment is fixed. However, we realized in the very beginning, we introduced those examples like the Go or StarCraft, and all those games opponents are not fixed. We're not playing against some fixed AI. We're competing with other human players. They can adapt. They can change their strategy over the course. Like they can even change their strategy during like the world championship, during the final. So it's not a good assumption to assume they're fixed, and single agent reinforcement seems not directly applied there. So there we come to the multi-agent reinforcement learning. We know it involves both game theory and reinforcement learning. But as we will argue today, the area is actually a lot more than just simple combination of those two. So we say this field is actually a very new field, and it's much less developed than the two classical fields like game theory and reinforcement learning. And also the new field, the multi-agent reinforcement learning, has a lot of its own unique challenges and opportunities we will also see today. Okay. So the task today is we want to establish a solid theoretical foundations of multi-agent reinforcement learning. Of course, it's not going to be that solid as already established game theory and reinforcement learning, but we want to start from the very basic and what we can do from those basic settings. And to differentiate the results or the material I'm going to present today from the very classical game theory is about a lot of focus on this efficiency. So we will actually pay a lot of attention on the sample efficiency and the computational efficiency. The reason we care about those is that in modern reinforcement learning or modern multi-agent reinforcement learning, actually those efficiency matters a lot. For example, when you want to train an agent for playing Go, AlphaGo 0 already trained on this Google cluster, which has thousands of computers. It's already trained on more than like 10 to the 7th games. Okay, so it involves huge number of samples. It also, the entire training is took more than a month. So basically, you want to train at school, probably you can do it just because we don't have computationally efficient algorithms so far for those kind of models. So that's why our theory not only involves statistics, but also involve computer science. So we want to have both statistical efficiency and computational efficiency. Okay. So I hope I already give you some good slides to motivate you to pay more attention to this multi-agent reinforcement learning. I guess this is like a theory workshop, so I will not do too much about other motivations. We'll directly jump into our theoretical frameworks. So to establish the basic theoretical frameworks for multi-agent reinforcement learning, I will cover the following parts. First one is about the formulation and objectives. So we know normal form games and extensive form games are no longer enough. So we will introduce a new model, or maybe not new model, but it's just different model, which already exists for a lot of years. And what is the learning objectives in those models? And then we will first talk about the approach, which is, we said, a direct combination of existing game theory and the single agent reinforcement algorithms, which is actually commonly used in practice right now, because this is just some simple strategy which you will first think of like when you consider these problems. And we will actually see why those methods may not be very desirable and what is the problem with those methods. Then we will start from the very beginning. We will talk about the most basic setting, that is two-player zero-sum Markov games. And we will also focus on the basic setting about the tabular setting. And we will see how we establish the solid result for this kind of scenario. And then we will go beyond the zero-sum setting to the multi-agent general sum setting. Okay. And we will see what's the difference and how we deal with this difference. And finally, we will also talk a little bit about the topic, if we have advanced topics, if we have time, like including function approximation. I bet Dylan already talks a lot about this kind of thing when we have a huge state space and how we deal with, how we do this reinforcement learning. We need a lot of function approximation techniques. We will also talk a little bit about the partial observability and conclude of the talk. Okay. Any questions so far? I guess also this is like a boot camp. So in spirit of boot camp, I will try to make everything simple. And if you have any question, feel free to interrupt me at any time. So first about the formulations and objectives. So we said we no longer, the normal form games and extensive form games are no longer good for study multi-agent reinforcement learning. So the model we're going to study is, instead of a Markov decision process, we're going to study so-called Markov games, or in the literature, also called stochastic games. So this stochastic games is introduced in Shapley 1953. It can be considered as an extension of Markov decision process to multi-agent scenario. I hope you're already very familiar with Markov decision process this morning. So just be quick about all the notations. So here, for simplicity, we first introduced the two-player zero-sum version of Markov games. And this Markov games will consist of following elements, that is states, action, and the transition and the reward and the horizon. First, this curly S is a set of states. And this curly AB are the set of actions for the max player and min player, because we're playing two-player zero-sum games. So assume one player is the max player, the other player is the min player. And we also have transition probability, that is condition on the current states and the action of the both player. And what is the probability distribution we're going to transition to the next states. And finally, the reward. Because this is zero-sum game, we can only specify just one reward, which is a reward for the max player, but also the loss for the min player. We can think the reward for the min player is the negative reward for the max player. Okay. Reward also depends on the states, action of both players. And finally, H is the horizon of the game. So we consider the episodic setting, same as what we had introduced this morning. So we assume the game will always ends at step H. Okay. So this introduced the elements of Markov games. So how we play Markov games. This is the interaction protocol we specify to play Markov games. We can consider, for example, we're playing a StarCraft, which we can model as a Markov games. Environment always sample some initial states. That is, we're kind of start from the beginning of the game. Then for each step, H from 1 to H, that is for each step how we play the game. First, both agents, me and my opponent, will take some action simultaneously. That is, I'm going to click mouse to someplace, and my opponent probably also click mouse to move some units. And then both agents will receive their own immediate reward. So this is both agents take action simultaneously, and then both agents will receive their immediate rewards, which max player is plus reward, and min player is minus reward. Then the environment will, based on the current states and the two actions both player takes, and transition to the next states. Okay, that is H plus 1. Okay. And we will first say what is revealed to the player. In this case, when we both take actions simultaneously, the agent is able to observe the action taken by the opponent. And also, when we transition to the next states, the agent is able to observe the states of the game. So that is, in this talk, we will mostly focus on the fully observable tabular Markov games. In the very end, if we have time, we will talk about some more advanced settings. Okay. So what do we mean by fully observable tabular Markov games? The fully observable means we actually have joint actions and states. Both are fully revealed to both agents. So there isn't any partial observability, and the entire state is hidden. The entire state is observed by agents. So for example, when applied to StarCraft 2, if some of you played StarCraft 2, you probably know there are some war frogs, so that you are not able to observe what your opponent is playing. And when you play poker, you are not able to observe what your opponent's card is. So for simplicity now, we don't assume we have partial observability. So we just observe everything. The second thing is about tabular setting. Tabular setting is assume the number of states and number of actions are all finite and small. These are very basic settings. You may wonder, okay, this may not be applied to practice, very applicable to the current practice. But we will argue this is actually serve as a very foundation for more advanced setups in the future. So if we want to understand, for example, the rich observation setting or like the large state setting, function processing setting, I think the very basic step, we always need to first understand what we can do in a tabular scenario and what we can do in the fully observable setting. Okay. And a few concepts similar to what we have been talking about this morning. One is about the policy. I guess in a single agent scenario, we most talk about the Markov policy. That is, without loss of generality, we talk about the max pair. So the type of Markov policy is the policy which only depends on the current states. So I observe what is current states and I make decision based on the current states. So it's a map from current states to the probability simplex of action. So this assumes we can play a stochastic policy. That is, we can actually play a distribution of algorithm. In reality, I just sample an action from this distribution. And the ability to place randomized action is very important in here because in game, we always need to play random strategy to be able to converge to Nash equilibrium. We will also talk about another class of policy that is called general policy. Okay, by the name, you'll see general policy may not be Markov. So the biggest difference is this class of general policy may not necessarily only depend on the current states. It can possibly also depend on the entire history. So based on the mass formulation, it is a map not only from the current states, but also the states action pair from the entire history. That is state action pair of all the past steps from the first step to h-1 steps, and map this entire history to some distribution of actions. In a single agent scenario, we can always, like in MDP, we can always say without loss of generality, we can consider Markov policies. But here we will see in Markov games, it's not always necessarily that case. There is some case we have to talk about general policies. And also, we define this max policy in this way, the policy for max pair in this way. We can also define the policy for the mean pair by symmetry. It's pretty simple. It's just change the distribution as probability simplex over A to probability simplex to B of B. Once we have definition of policies, then we can talk about the values. Value is only defined on the joint policy. That is, I have to specify both the policy of the agents and also the policy of the opponents. Then we can talk about the value. Value is the expected cumulative rewards received by the max pair if both agents follow this joint policies. So the definition is basically I'm gonna summation the rewards from the very first step to the very last step. So this is total rewards I'm gonna receive when I play the game. And if the both pair, I'm gonna take expectation over pi because both pairs going to play by the policy pi. And this is my value. Okay. Any questions so far about the basic formulation?
So players do players know about their opponent's policies?
Oh, they don't. They only observe opponent's actions.
I see. Okay.
That's a good question. Thanks. Okay, and we are introduced the model of Markov games. We can consider how expressive this Markov games is, and we just note first some special cases. First one is the normal form games. Okay. It's very simple. We realize normal form games is a special case of Markov games, just because we can make Markov games with just a single states without any transition. So we have only single step. Then this Markov games will reduce to the normal form games. And it is also extensive form games is also a special case of Markov games. We can basically embed an extensive form game into Markov games by restrict the transition structure to must be tree structure. So that is whatever I start from the different states, I cannot end up with the same states. So this is a property for the extensive form game, but it's not necessarily required in Markov games. In Markov games, it's possible I start with two different states, and then I take some actions, I end up with the same states in the next step, which is also the case, for example, for StarCraft, for Go, for some different games. Okay. After we clear about the class of the Markov games, the formulations, then the next question we're going to consider is what is the solution we're trying to find? In a single agent scenario, in a Markov decision process, it's very easy. We just want to find a policy which maximizes the cumulative rewards. However, here it's become more complicated. Let's just consider what is the, for example, the problem of Go. Like we want to develop AlphaGo. So what is the ultimate objective we want to achieve for designing this very good multi-agent reinforcement learning algorithm? Do we want to beat the world champion by a large margin? Is this policy good? Or do we want to beat all the players by a large margin? We clearly know that second objective probably is just not possible, because we can just always play back against ourselves, and we cannot win by a large margin. And the first objective, win the world champion and by a large margin. So this is more or less a concept of the best response. So best response is also, we also have a concept of best response in the normal form games. So it's a similar concept in the Markov games. So best response is a policy which best exploits the opponent's policy. So in our notation of Markov games, we have a value that is depends on the policy of the max player and also the min player, that is pi1 and pi2. So the best response of the pi2, the policy of the min player, is just the policy which maximizes the value of this b pi1 pi2. So we know that a special case of Markov game is like a normal form game. We already know the best response of in the rock paper scissors is like very easily understandable. It's like best response of rock is paper, best response of paper is scissor. And in the complicated games like StarCraft, we also have like similar concepts like rock paper scissor. For example, there might be 3 strategies in the very beginning. You can do some normal opening, you can do some fast expansion, you can also do some fast attack. And these 3 strategies like rock paper scissor, they kind of beat each other in a loop fashion. However, we know there are some drawbacks about the best response. Best response is very good against a fixed opponent. For example, if our goal is really just want to beat like some fixed world champion, like just one single person, then this way is very good. We just find a very good policy that exploits the weakness of that opponent. But however, the best response may not be very good against other players. Like we all know in rock, paper, scissors, the best response of rock is just a paper, but it's not very good against scissors. So now we turn to another concept that called Nash Equilibrium. I guess is very familiar for all the audience in this bootcamp. Nash Equilibrium is like a very famous concept in normal form games. In Markov games, we can also define Nash Equilibrium as the same way as normal form games, which is just no player has an incentive to deviate from their current policy. For example, here for any, we say pi1 star, pi2 star is a Nash Equilibrium. If when you fix pi2 star, fix the policy of the min player, it already achieved the maximum for the max player. Okay? So the value will be greater than the value of pi1, pi2 star for any pi1. At the same time, when you fix pi1 star, the policy of the max player, it also achieved the minimum value for the second player, for the min player. So it will be less than the value of the pi1 star, pi2. We all know in the normal form games, there's one very famous theorem called the minimax theorem. So in reality, for for 2-player zero-sum Markov games, the minimax theorem still holds. We have the minimum over pi1, max over pi2, min max over strategies. The value is equal to the min, the max min value is equal to the min max value. However, we notice several differences. The first one is in the normal form games, you require this to be mixed strategy. Here it's sufficient, we just make it to be a single policy. It's okay, because policy, we already make a random policy. So policy in some sense is like similar to mixed strategy. On the other hand, we also want to comment a little bit. This theorem is actually not due to directly due to von Neumann's minimax theorem. The reason is this structure is much more complicated than the normal form games. Von Neumann's minimax theorem kind of like says for any function which is convex concave, you have minimax theorem holds. However, you can prove for Markov games, this v pi1, pi2, this value function is a function of both policy, but it is not a convex concave function of pi1 and pi2. That is, fixed on pi2 is not convex on pi1, and the fixed on pi1 is not concave on pi2. However, this minimax theorem is still true because you can basically prove it by dynamic programming. And for each state and step, you can say von Neumann's minimax theorem true. And then you can do the dynamic programming, and you see for the entire Markov game, this minimax theorem still holds. Okay. So the good thing about this minimax theorem is that this also gives another interpretation of this Nash equilibrium, why we want to learn Nash equilibrium in Markov games. Because Nash equilibrium is now a policy which is optimal when we always facing against best response. Okay. So basically here, there's no difference between stack equilibrium and Nash equilibrium in our two-player zero-sum games. And it is an optimal strategy in the min-max sense. It's also optimal in the max-min sense. Like for example, for rock, paper, scissors, it's optimal because no matter what my opponent plays, I will never lose. So my opponent will never gonna exploit me. So the strategy we're gonna find is not going to beat anybody by a large margin. We may not be able to win anyone by a large margin, but the strategy we're going to find is going to guarantee nobody gonna beat us. Similar to a normal form game, this is the final goal we're gonna find. So our objective in a two-player zero-sum form and zero-sum games is going to find epsilon approximate Nash equilibrium, which we denote as pi1 hat, pi2 hat. Our objective is we want to find this objective Nash equilibrium using a small number of samples, which has a very mild dependency on the states and actions S, A1, A2, and epsilon and H. So it should be AB, and basically the number of actions of both players. And in terms of mathematical definitions, so this requires the epsilon approximate Nash equilibrium basically is the duality gap, which is similar to normal form games, is less than epsilon. We know that for the exact Nash equilibrium, this duality gap is equal to 0. So for approximate Nash equilibrium, we allow this to have some epsilon tolerance. Okay. Any questions so far about all the setups? What is the objective we're trying to find? So I guess so far it seems like everything is similar to normal form games, and we just have different notations and maybe with slightly different proof, but all the structures remain similar. But I will name a few challenges which makes the algorithm we're going to design fairly different from this classical algorithm for normal form games. The first one is a large size of policy space. Okay, so Markov policy is defined as even consider Markov policy in the tabular setting is defined as we need to choose a probability distribution over actions for all the states at every steps. Okay. So the number of possible Markov policies is 1 over epsilon to the HSA if you consider covering number. And if you just naively treat this Markov game as like a super large normal form game, then your pure action, the action you're going to take, is going to have this amount of size. So basically, any algorithm you're going to use for normal form games directly applying on Markov games will incur a huge amount of sample complexity or like computation complexity, which is not feasible in practice. And the second interesting part is Nash equilibrium. We can prove Nash equilibrium strategy is always Markovian. It is a Markov policy. However, the best response may not be the Markov policy. This will also introduce a lot of complications because it may not be very easy to find the best response in this scenario. And finally, also because what we have in the second part, we talk a lot this week about solving games by no regret learning strategy. However, one very big difference of Markov game from a standard normal form game is Markov games do not allow any efficient no regret learning algorithms. This is proved in our paper by Yu Bai and Tiancheng Yu in 2020. So basically what we are saying is if you're able to do no regret learning for Markov games, you're gonna solve like learning parity with noise in polynomial times. So it's a computational hardness results. The major reason there is by doing no regret learning, you're gonna need to do finding best response of your opponents. And although the game is Markov game, so the game has Markov structure, your opponents need not to play Markov's policy. So they can play some complicated like time-dependent policies. The first step is gonna depend on the last step. So in those scenarios, learning the best response is kind of like very difficult. Like you need to infer some like long-time correlation, which gonna incur some time, which is exponential in H. It's all because this like a sequential feature. We have like H steps, and we want to avoid this exponential depends on H. So a lot of things becomes different. Okay. So any question about until now? This basically concludes about the formulations, and I kind of briefly talk about the challenges. Later on, we will talk more in detail about what is specific challenges and how we address them.
So I have two questions. One is the epsilon that you're showing, the large size of policy space. This is 1 over epsilon, and this epsilon refers to what?
Oh, it's just like I want to do an epsilon cover over the Markov policy. Like because the Markov policy, because the policy is like you map to the probability simplex, right? You kind of take a random action, which corresponding to choose a probability distribution over action. And so
this is the discretization over this space of actions.
Right.
Okay.
Discretization of the space of
probabilities.
Yeah, probability distribution over actions.
Yeah. And then in the bottom you have alpha. What is this alpha?
Oh, this is just saying no regret. I define no regret learning in terms of I'm going to compete with the best policy in hindsight, and I'm gonna retrieve some regret, which is a sublinear, which is standard definition of.
Right. So you can achieve it, but there is no good algorithm, or you cannot even achieve it.
You can achieve it, but it's not efficient. So
in terms of H.
In terms of H. Yeah.
Okay.
This is what I mean by efficient and no regret learning. So what I'm saying, we cannot achieve this. We cannot achieve poly H, I say. We will have some exponential H here. Oh, sorry. Here, what I mean is like, in order to achieve this no regret learning here, we need some computational inefficient algorithm, which is a skew exponential H. This is what I mean. But later, we can talk about some transient version of this result.
So one question I had, and there's also one question in the chat. So I guess many, like even in contextual bandits, like if you don't make some Oracle assumptions, things will be super hard for this setting. So is there some Oracle impossibility result here? Like even if you have some best response Oracle, you can't get no regret learning. Like if I give you some Oracle heuristic, could you achieve no regret?
I guess the hardness here actually exactly lies in the best response is hard. Just because I said the best response may not be Markov policy. So it's possible your opponent is always playing Markov policy, but because he's like playing 2 rounds of Markov policy, so the mixture of them is no longer Markov policy. And you're competing with the best response of a non-Markov policy. Essentially, you're competing with the best response of a mixture of Markov policy, which is like a history-dependent policy, and it's very difficult to compete. Sorry, no, I'm saying the wrong thing.
And Costa's asking is, what if you restrict your opponent to Markov strategies?
Even if you restrict your opponent to Markov strategy, no learning is still hard. Basically, the reason I said is like, although the opponent is like can play Markov policy at every iteration, but when you have 2 rounds of Markov policy, your opponent is effectively playing a mixture of Markov policy, which is not Markov. Thanks. So let's continue. So we will first talk about some. Yeah, okay, go ahead.
Sorry, I didn't understand why the Nash Equilibrium policy is Markov. Can you explain that?
We will talk about this later, but basically you can prove it by dynamical programming. We haven't come to that so far, but this is like just some challenge which I want to spice you to be interested in this problem. We will come to some of details later about this. Thank you for questions. First, we will talk about some simple stuff about some direct combination of what existing algorithm for game theory and what do we have for single agent reinforcement learning algorithm. So this approach, this direct combination, is all relies on like a very key observation. That is, if we're gonna fix opponents, if my opponent is fixed, then computing the best response is kind of like a single agent reinforcement learning problem. Like because if my opponent is fixed, then opponent's plus environment is just big environment. I can view it as a single environment, and I can use single agent reinforcement learning to do it. So the style of this algorithm kind of like it's like hybrid of the two algorithms. The first one is a standard Nash finding algorithm for normal form games. A very important part is this Nash finding algorithms must be this best response oracle-based Nash finding algorithms, because eventually we want to reduce to only finding best response. And then we're solving the best response steps. We just use whatever single agent reinforcement algorithms. So the commonly used like those Nash finding algorithms in the multi-agent reinforcement learning setting is like cell play, fictitious play, and double oracle. There are also PSRO, which is like some extension of double oracle. For simplicity here, we just do double oracle. And a single agent algorithm reinforcement learning, you can use any algorithm didn't introduce this morning, like value iteration, Q-learning, and deep Q network, which is a deep learning version of Q-learning, and also some policy optimization, like proximal policy optimization, PPO, TRPO, a lot of them. Okay. This actually is a fairly common strategy used in practice. And if you have ever read like Alpha Star, which is the like technical notes or like the paper, and DeepMind posts on like what are their strategy in solving like finding like to train their agents for StarCraft 2. It's kind of like vaguely following this high level framework, following this strategy. Let's first talk about this like Nash finding algorithm with the best response oracle. First one is cell play. Cell play is an extremely simple algorithm. Some first thing you can think of. Basically, we have two players. The first player first find the best response of the second player, and then the second player again find the best response of the first player, and then first player find the best response of the second player. You kind of alternating between those two. We clearly know this is not a very good strategy, because in rock paper scissors we can know like even in the normal form games, if this algorithm will just looping around like rock paper scissors, those like single strategy forever. This do not converge to Nash equilibrium, even in the very basic normal form games. And second, we also realize averaging would not help, basically because although kind of like, rock paper scissors, we're kind of like looking around, and one third probability doing averaging is the right thing. But what we can do is we can just slightly change the reward matrix for the rock paper scissors games. For example, if you win with rock, you probably won't get reward 1, you get reward 0.9. This is sufficient to shift the Nash equilibrium to be deviating from like one third uniform distribution for rock paper scissors. But if you play cell play, like you just do this cell play algorithm, you will still converge to the uniform distribution to averaging. So averaging is not enough to fix this problem. So this algorithm just not very good. The second one is fictitious play.
There's one more question.
Yes, go ahead.
All right, this may be a dumb question, but I thought we didn't have access to the other player's policy.
Oh, so we kind of like with okay, in the interaction protocol, we don't have access to the other player's policy. This is like when we play the game. But there, what we talk about is like training process. So okay, what I'm saying is in the test process, you don't have access to your opponent's policy. But in the training process, it's possible like you do some like cell play training. Okay, that cell play is different from this cell play. So basically, when for example, when we train Go or when we train for StarCraft, we can definitely control both agents and let them learn together. So in this way, we can reveal the policy is okay. So basically, my answer is like in the training process, you can communicate about all the policies. You can do whatever the way like two players can even collaborate to like learn the Nash equilibrium together. And thank you for the clarification.
Actually, now I'm more confused. So we have not talked about training, testing, nothing, right? So what is the model you're working on? I mean, can you
the model? Okay,
in your model specifically, you said that we don't assume anything about the opponent. There was nothing about test or train.
Okay, so the interaction model is like this, and okay, so there are two parts. The first part is the training parts. Okay, let me clarify about training and test. In the training parts, we're going to able to like basically two pair can collaborate and they can do whatever, and they can communicate on all the information. They just need to interact with the protocol, or interact with the environment with this protocol, but they can talk about anything they want. All the information they have, share all the information they have. But what I mean by test is like eventually you find a Nash equilibrium. And so, for example, I train myself by StarCraft for like a month, and eventually I come up with a policy. But eventually I'm gonna test, that is, I'm gonna play with some world champion, or I'm gonna play with some other opponents. And when in this phase, when I play against other opponents, I'm not gonna observe what is policy of the opponents.
When you say training, you basically mean just the computation of the equilibrium, right? It's just like a decentralized algorithm that computes the equilibrium, can do whatever with both policies, and then eventually the two players are going to play based on those policies. But when you compute the equilibrium as a centralized algorithm in your computer, you can look at what is your current guess for players 2 policy, and design a policy for player 1, and so on and so forth, and iterate until you find an equilibrium. And now they play based on that.
So basically, during training, you assume that you know the policy of both players.
During training, basically means just computing the equilibrium. Like the algorithm computes the equilibrium of this Markovian game. But when they play the game, they're going to play based on these policies that obey this interaction protocol.
The only thing, Vasilis, is there's a difference between computing the equilibrium when you know like the probabilities and the rewards and so forth, and computing the equilibrium when you only see like trajectories.
Okay, yeah, that's a valid, yeah.
Yeah, we'll also talk about that later.
But then I think, so far we haven't talked about anything about unknown or stochastic or, right? So that's why I was saying that at this point, it's more like a computation, like someone gives you a transition, like a world, and you're trying to calculate an equilibrium.
Right, and I will just say a little bit more about when we talk about the case, we observe only samples, and we also have like training and test phase. Like training, like when we observe the samples, we also want to just find a Nash equilibrium, but based on the samples. And in those scenarios, two players can also communicate.
I think the training testing maybe makes more sense as a keyword for the sample-based situation.
Yeah, but I think it's you're right. I think it's probably the field also terminology this as like a centralized algorithm, but we could also have decentralized algorithm, which like players don't communicate even in the training phase, and we will actually also come to the algorithm like that later in this tutorial. Okay. A very good question.
Yes. Can I add something to this discussion? So here, my understanding is that you're basically computing equilibria, right? But if I think about the AlphaGo example, the idea is it's not even sure that if I want to beat professional, I really want to use the Nash equilibrium strategy. I want to use a strategy that does well against whatever I think it's, against maybe a variety of strategies, if I think, of course, that my rival is not going to play Nash, right?
Right. So I think this is like go back to the very beginning, like about solution concepts. What you talk about is you want to find a probably best response or some super best response to a class of policy, but you don't want to find Nash equilibrium.
Exactly. I guess a good algorithm in this case would be an algorithm that sort of figures out what policy my rival is using and best responds to that. I think, assuming that my rival's policy is fixed, right? So that's
So there are two parts. One is like there are two objectives, I would say. One is about Nash equilibrium, which is like defend against optimal player, and the other one you said is you want to exploit some suboptimal play of the opponents. I think that one is more related to no regret learning, and which is very difficult in Markov games. Maybe you cannot exploit it very well, but it's different concepts, and which is not what I'm talking about right now. But it is a very important thing. Yeah, I agree. Okay, those are all very good discussions. Thanks for raising that. Okay, so after cell play, we talk about fictitious play. Fictitious play is similar to cell play, but instead of just you're gonna find a best response of the immediate policy of your opponents, you first do an average policy of your opponents, and then you find a response to that to be okay. So the max player is going to find the best response of the average policy of the min player, and then min player is going to find the best response of the average policy of the max player. So this is a so-called fictitious play. When you inspect a fictitious play on rock, paper, scissors, it seems like it's making more sense, at least making more sense than cell play. And in fact, there are some asymptotic convergence guarantee about the fictitious play, which is by Robinson in 1951. It says fictitious play indeed will converge to Nash equilibrium, which is also heavily quoted by a lot of practitioners, which justify why they want to use fictitious play, for example, when they train on multi-gene reinforcement learning problem. On the other hand, as a theorist, we will of course not only have, we will not be happy about only convergence. We will ask that next question: how fast? Like how many iterations we need for this fictitious play to find Nash equilibrium? So if we inspect a proof of the Robinson 1951, it actually says it requires something 1 over epsilon to the omega A iteration. A is like the number of actions in normal form games to find epsilon Nash equilibrium, which is exponential in the number of actions. This clearly doesn't sound very good. So Carding conjectured in 1959 whether this may not be just artifact of the analysis, maybe fictitious play actually doing better. So whether this really can be improved to some 1 over epsilon squared to find epsilon optimal Nash. So Costas, also in the audience, he kind of in 2014 he refuted this conjecture. And he basically shows this 1 over epsilon to the omega A is kind of like real in some worst case scenario, which basically fictitious play is not guaranteed to convert fast, even in the normal form games, not mentioned about Markov games. This we pass. Finally, we talk about double oracle. So clearly there's something better we can do than fictitious play. Fictitious play basically just compute the best response of the uniform weight of your opponents. And what if I'm allowed to do some like a more sophisticated weighted average of the opponent's strategy? So one way to do weighted average is by inspecting the reward matrix of a subgame. So this subgame is consisted of all the rewards. That is each row is a policy of the max player played in the past, and each column is a policy of the min player played in the past, and the entry is basically the value of playing that game. So this is like a reward matrix for the subgame where you can only play those policies that has already been played by the max player and the min player. So what you can do is you first find the Nash equilibrium of this subgame, and then you use this Nash equilibrium, which is a mixed strategy, and you use this Nash equilibrium as a mixing policy for your to like compose your opponent's policy, and you find the best response of that. This is a double oracle algorithm. So what is the theory of double oracle algorithms? I want to talk about double oracle algorithm here is just to represent a general approach where you kind of do this weighted average of the opponent's policy, but it's not necessarily finding Nash. It can be some other stuff, but finding Nash is one of the good way we can do this. And there, in fact, is some convergence guarantee about Nash double oracle algorithm, which says it can find Nash equilibrium in normal form games with A actions, with A actions in order A iterations. This looks better than fictitious play. However, if we inspect why this guarantee is true, it's basically because every time, if you guarantee in a normal form game, there are 2 scenarios. One is like you compute the best response, you compute some new action which has not been like played before, then you kind of adding that action to your subgame matrix. Or if you don't have any new actions, your best response is your old actions, then you already reach Nash equilibrium. So if you, in the worst case, if you haven't if in every iteration you encounter a new action, then in A iterations, your matrix MK is going to be the entire game matrix for normal form game. So that's why you're always going to end in all A iterations.
See, there's a question, clarification.
Doesn't the value depends on the states? Yes. So I haven't talked about. So here, what I'm saying, the value here is just if always start from the very beginning, I define it way. But you're right. Like for Markov policies, and you can also define the value if you start from some intermediate step that would depend on S. Here, I don't have any S dependence. Just says the entire value is like the entire rewards, all the cumulative rewards. Start from the very beginning with the initial distribution. Initial state sample from initial distribution. And also, if on the other hand, if we directly convert a Markov game into a normal form games, we see like the action is kind of equivalent to a policy in Markov game, which we already says we have like 1 over epsilon to the HSA prime in Markov games, where this A prime is the number of action in Markov game, which is the size of policy space. It's exponentially large in HSNA. So doing this is not a very efficient way to solve the Markov games. So we just summarize some drawbacks of this direct combination approach. One is this algorithm is those line of algorithms trying to design based on some black box usage of single agent reinforcement learning and normal form games, which doesn't exploit too much about the structure of Markov games. So basically, they still treat this game as a normal form games, just with complicated actions. And the second, we already said converting this Markov game into normal form games would give like huge number of action pure strategy, which is like very inefficient for all the existing algorithms to work. And then finally, there's another factor I haven't talked about, which is finding best response may not be an easy single agent reinforcement problem as we think. The reason is come back to again, we talk about the possibility of opponent is playing non-Markov policy. When opponent is playing Markov policy, of course, in the view when, like for example, when main player is playing Markov policy, in the view of the max player, because the environment transition is Markov and opponent is playing Markov policy. So in the eyes of max player, he just feels like he's playing Markov decision process. So that's why we can use single agent algorithm. But when your opponent is playing non-Markovian policy, then even in the eye of max player, you can see the structure and the game is no longer reduced to a Markov decision process. There's actually some correlation between like the first step and third step, even conditional states of the second step. And the reason we talk about non-Markovian policy is because if you go back to see all the algorithms like double oracle and also fictitious play, they always play some mixed strategy of the policy they played earlier, which is a mixed strategy of the Markov policy, which is non-Markov. So that's why in those games it's necessary to study this scenario when the opponent is playing non-Markov policy and you are no longer solving MDP. So in theory, like V-learning, like Q-learning and value iteration, those kind of basic algorithms should not work. Their theoretical guarantee should not directly apply here.
Just a clarification about these non-Markovian policies. Can I redefine the state space? I mean, if I remember your definition, the non-Markovian policy was depending on the entire history. Mm-hmm. But can't I have that the state summarizes the entire history? So if I redefine the state, I can only...
You can, but it's inefficient. So if you define the states as an entire history, then your number of states is something exponential in H. Okay. Which is something you don't want. I guess I will stop here for the first hour. If you have any questions, feel free to ask. And then we finished all the basic setup and talk about some nice approaches. In the next hour, we will talk more about okay, we now know a set of like not very good solutions. What is a good solution? Like how are we going to solve these problems?
Any questions?
Sorry, I might have missed this, but can you explain which games does this model model well?
Model well.
Like, yeah, which types of games?
I think it's okay. So first, it's for all sequential games, and I think the biggest difference of this game and extensive form game is this allows states to be shared, like it allows the transition to have graph structure. So basically, you start from two states, you might end up with the same states in the next step. So I think like StarCraft or StarCraft with some partial observability, but if you say like there's no partial observability, like Atari games with 2-player, I think they all like fall in the category of Markov games.
Sorry, I guess I'm just asking because it seems like from one state we can only move to one single other state.
No, you can move to a lot of different states. It's a transition distribution. So, it's the same as a Markov decision process. So from a single state and some fixed action, you have a transition distribution over next states. That is, you can possibly transition to all states, but with some fixed distribution. It's specified by this transition probability. Is that a question you're asking?
Great. Thank you, Chi. Thanks. And we'll be back in half an hour. Thank you.
Thank you. Bye-bye.
Yeah,